Good afternoon, all. Welcome to the second session of Summer School on Algorithms. Before moving to the session, here are a few reminders. All participants, please make sure your mic is muted during the session. And if you have any doubts or queries, please post those in Sulip chat under exact exponential algorithms stream. Okay. Today, we have Dr. Pradeesha Ashok. She is an assistant professor at IIIT Bangalore. She did her PhD from Indian Institute of Science, Bangalore. Her research interests are broadly in theoretical computer science and specifically in computational and combinatorial problems in geometry. She is also interested in research problems in algorithms, graph theory, and combinatorics. Prior to joining IIIT Bangalore, she was a postdoctoral fellow at Institute of Mathematical Sciences, Chennai. Today, she is delivering a talk on exact exponential algorithms. Welcome, Dr. Pradeesha, to give the talk. Over to you, ma'am.
Thank you, Arsha, and to everyone. Yes, so as it was mentioned, the talk is on exact exponential algorithms. And yeah, so please feel free to stop me, or if you have a question, please ask it. I mean, Varsha announced Zulip chat. You can, while the talk is going on, you can also ask on the Zoom chat, whichever is comfortable to you. But please make sure that you understand. Okay, so the topic is exact exponential algorithm. And I'm assuming all of you have done at least one course in design and analysis of algorithm. And most probably in your first course, most of the algorithms that you have studied, designed, discussed were all polynomial time algorithms. And exponential time algorithms is something that you try to stay clear of. But the same course, the first course, you have also probably seen something called as NP-complete problems. Right. So in NP-complete problems, we know by definition or the implication of a problem being NP-complete is that you don't expect to solve that problem exactly in polynomial time, right? And as you all know, NP-complete problems exist, and there are a lot of them, right? So you encounter a large number of NP-complete problems in your day-to-day life even. So it is important to solve them. And in the morning session, you have seen Professor Murli talking about how to solve NP-complete problem approximately. Right. So this talk will be about how to solve NP-complete problem exactly. Now you know that if you are looking for an exact solution for all instances of a particular NP-complete problem, you have to admit exponential running time algorithms, right? Otherwise, you have proven that P equal to NP. Right? Okay. Okay, so we are trying to solve NP-complete problems in exponential time. So we'll see more of this topic later also. Like tomorrow, we'll talk about the parameterized algorithms, which is again some kind of special type of exponential algorithm. And later, Wednesday and Thursday, you can hear to Professor Saket Saurabh talking about parameterized streaming algorithms and parameterized approximation algorithms. So today it's like the first session in this series. Okay, and today we will just discuss how to design exact algorithms. You might ask, why is this interesting? Because every problem can be solved in exponential time, right? Do you know a problem which cannot be solved in exponential time? Okay. Like even if you use brute force. Now, what do I mean by brute force? Is I'll take a problem and I'll consider its solution space. I'll go through or I'll search its solution space exhaustively. One of them is my solution and I find it. And this takes exponential time, right? Right. For example, let's say that you are Your question is, you are given a graph, and your question is, find the minimum sized vertex cover, right? So what is the brute force solution? The brute force solution, you generate all subsets of the vertex. Okay, so generate all subsets of G, of V, of G. Okay, and for every subset, check whether it is a vertex cover or not. Okay, can we check whether a subset is a vertex cover or not in how much time is needed? Okay, so a vertex cover is a subset of vertices such that every vertex has a has at least one endpoint in vertex cover. So you can check, given a subset, you can check whether it is vertex cover or not in polynomial time, right? So this can be done in polytype. Okay, and you do this for every subset, and of the subsets which are actually vertex covers of G, you will return the minimum cardinality one. Right. So this is the brute force. This you can do for any problem, right? Any combinatorial problem, you can do this. So how much time? Yes. So how much time did I spend here? So this is some polynomial, and how many subsets of V are there? There are 2 power n subsets. So the running time of this is 2 power n. Okay. So any combinatorial problem you take, you can solve it using this method, what you call as the brute force, right? Okay. So the question here that we ask in design of exact exponential algorithm is, how much better than exhaustive search can we do? Okay. For example, suppose there exists for a problem, the exhaustive search takes n power n time. The question is, can we find an algorithm that runs in 2 power n time? See, 2 power n is again exponential, but it is a better exponential function than n power n. In fact, it is a much better exponential algorithm or exponential running time than n power n. Right? Okay, so this is our aim. Okay, so we'll start with a problem. We know that, or we don't expect polynomial time running time, but we will solve it in exponential time exactly, and we'll try to get the best possible exponential running time. Suppose for a problem, you are able to improve the brute force from n power n by a new algorithm, which takes only 2 power n. What can you do next? So once you have a 2 power n algorithm, I mean, you can look at running time like, can there be 2 power root n algorithm? Or you can even look at algorithms which is like 1.9 to the power n algorithm. Then asymptotically much faster algorithm than 2 power n. Right? Since we are working with exponential function, even if we improve 2 power n to 1.9 power n or 1.9999 to the power n, it's asymptotically a better running time. And also practically also it's a better running time. Okay. Yeah, so that's the purpose of this talk. I hope all of you are motivated enough. So the field of exact exponential algorithm, it's pretty young. There are topics or there are techniques for designing exact exponential algorithm that's being discovered now also. Okay. So in this talk, we'll see some basic techniques that can be used to design good exponential algorithm. Now, what do I mean by good? I already explained it. Right. And yeah, so the most of the algorithms that we discuss is taken from this book. It's a book, nice book, which explains techniques for exact exponential algorithm by Fomin and Cratch. Okay, so we'll go to the first technique, which is known as a branching technique, also known as bounded search tree, branch and reduce, etc., etc. Let's call it a branching technique. Okay. In a branching algorithm for a problem. See, here also we are searching some kind of, we are doing an exhaustive search over the solution space. But the difference here is we'll reduce at every step, we'll reduce the solution space to be much less than what we had before. Let's do an example. So we'll consider this problem, the maximum independent set question. So in the maximum independent set question, we are given a graph, and okay, in a graph, an independent set is a subset of vertices such that two vertices which are pairwise non-adjacent. That means two vertices in the independent set do not share an edge. Now, your question is to find an independent set of maximum cardinality. Okay. For example, let's say that your graph is this. Okay, so this. Okay, so here any two or any pairwise non-adjacent vertices, like for example, you take A, E, F. Okay, so this is an independent set. They don't have an edge between them. You can even take B and G and F. Okay, so this is also an independent set. If you take A and H, this is also an independent set. Your problem is to find an independent set which is of the maximum cardinality. So here it will be B, C, D, H or A, E, F, G. So this is a NP hard problem. You don't expect to solve it in polynomial time in general graphs, but there are certain graphs, there's some special graphs which admits polynomial time algorithm to solve maximum independent set. For example, you might have seen trees. Okay, in your first course, you might have solved, or you might have designed an algorithm how to solve maximum independent set in trees. No, we don't need it here. Okay, so we are looking at a general graph. Okay. So in a graph, right? So here, at every point, at every step, we'll take a small part of the instance, the input instance. Like so, like let's say that I take this vertex A. I want to get the maximum independent set and have the vertex A. Right. Now I know there are two possibilities with respect to A and the maximum independent set. Okay, there are either A is part of my maximum independent set or A is not part of my maximum independent set. Right? Okay. So here I have a vertex V. I have only these two, and these are like exhaustive conditions, right? Either one of them, exactly one of them should be true. Right? It contains B or it does not contain B. Okay. So what I will do is, in a branching algorithm, we'll consider both these options. Okay, and we'll solve the rest of the problem for each of these options. Okay, so in other words, I'll call that I'm going to branch on these two options. Right? So I start with my graph G. Okay, and my algorithm has two options. One is I can add the vertex V to my maximum independent set that I'm looking for. Okay. And what is my next option? I don't add it, right? Or so I say discard. Okay. And I know that one of them is a correct option. I don't know which one, but let's say one of them. Okay. So what is the rest of the solution? If let's say this is the right answer, okay, that is my maximum independent set does not contain V. Can I find or can I express the answer of G, the solution for the graph G, using a solution for a smaller subgraph? I've already discarded V, right? So I've decided that V cannot be in my solution. So what is the rest of, what is my solution? So if V is not there, what I need is the solution for G minus V, right? Okay. And okay, so this is right. So if V is not in the maximum independent set, then what is the solution I'm looking for? I'm looking for the solution for G minus V. And how do I find the solution for G minus V? I can recurse on it. Yes, it is exactly recurse, right? Okay. So I can solve this by recursion, right? Okay. Okay. Now, what about the other option? Suppose the correct option is maximum independent set contains V. Then what do I know? I know that V is in the solution. So if V is in the solution, one thing I can say is that none of the neighbors of V are in the solution, right? Because I'm looking for an independent set. So I have V, I have added V to the solution, and these are its neighbors. So I cannot add these to my solution. I know that. Okay, and there is rest of the graph. Okay, so if V belongs to the maximum independent set, the rest of the solution is what? The solution, or you can say the solution is what? Solution is V. You have added V union what? G of, okay, what's the graph that I should look up now for finding the rest of the solution?
Sorry, ma'am, there is a question on a chat.
Okay. No. Yeah, I think G minus. Yes, I've already seen that. Thank you. Okay. So you cannot take G, you cannot take neighbor, you cannot take V, you cannot take neighbors of V also, right? So this is the solution of G minus V and its neighbors. So I'll write it as close neighborhood of V, right? Close neighborhood includes V and its neighbors, right? So I know that one of them is the right answer, and both I can find by recursion, right? And which of them is the right answer? Whichever is the maximum is the right answer, right? Okay, so this is my branching algorithm. So I start with a vertex, an arbitrary vertex, and I branch on whether to include that vertex in the solution or not include that vertex in the solution. Okay, and for on each branches, I've reduced the size of the input instance. On one branch, I've so let's say with G is n. On this branch where I have taken V, I have reduced it by the size of neighborhood of V. On the other branch, I have reduced it by 1. Right. And these two I will solve recursively. Okay. So this is like a simple pseudocode for how the algorithm works. V is any vertex, and and I recursively call the functions MIS again for G minus V and G minus N of V. The question? What did I want? I wanted to improve the running time. Okay, I forgot to ask this question. What is a brute force running time for maximum independent set? Should be easy. If I'm using, instead of this, if I'm using the brute force algorithm, what will be a brute force algorithm? Again, just like vertex cover, I'll take every possible subsets and right. Okay. So my brute force was 2 power n. So is this algorithm better than 2 power n? What is the running time for this algorithm? So we know how to analyze the running time of recursive algorithms. So let's say that T of n is the running time for solving an instance of size n. So what are my recursive calls? So solving MIS of G minus V takes time T of n minus 1, and this will depend on how many neighbors V has, right? So yeah, so this is the running time T of n It's given by T of n minus 1 plus T of n minus degree of V minus 1. Is this clear? Any questions at this point? Okay. Okay. So how big, how bad this can be? T of n, the solution of this recurrence. So while adding itself, can we check if it violates an independent set? No. When we are whenever we are adding a vertex, we are deleting all its neighbors, right? So a future addition will not violate an already added set. I hope I got your question right. Okay, right. Okay, thank you. Right. So how bad this can be? See, in the worst case, okay, bad cases is when degree is small, right? Like a recursion works faster if you if you reduce reduce the size of the instance very fast. So T of n minus 1 is that you cannot do anything there. How bad can D of V be? See, every algorithm you see in this talk is going to go exponential. And you cannot expect a polynomial time because this is an NP complete problem. The question is, can we improve the exponential running time to a better exponential running time? Okay, so we have a 2 power n, which is a brute force. Can we improve from 2 power n to something smaller? So we cannot expect polynomial. Okay. See, here I can say that, okay, the degree of vertex can be a 0 also, right? I mean, V can be an isolated vertex, so D of V equal to 0. So I'll say that, okay, if D of V is equal to 0, then what is this? This means it is T of n is T of n minus 1 plus T of n minus 1, which is again 2 power n. Okay, so this is not going to improve then. Okay. So now I'll ask the question, can the vertex degree be 0? Can it be 0? Of course, there can be isolated vertices. But if there is an isolated vertex, do I have to decide whether to pick it or not pick it in an independent set? Yes, right. So if it is 0, you can include it directly. Okay. Okay. So what if vertex is of degree 1? Right. So if I have a degree 1 vertex, something like this. So this is my rest of my class. What do I do about this vertex? Can I directly add it to the independent set or not? Leaf vertex. Okay, I mean, if you're saying that it needs a proof, right? Okay. Is it correct? I think it's correct. Okay. So, but what I'm going to say is, I'm going to say that, okay, in my algorithm, I'm always going to start with a vertex, right? I said V is picked is arbitrarily, right? So I'm going to start with a vertex. I'm going to pick a vertex V, which is of degree at least 3. Okay, so I'll go back to my algorithm and I say that, okay, let V be a vertex in V such that degree of V is greater than or equal to 3. And then I run the algorithm. Okay. Is it fine? What if there is no degree 3 vertex at all? Every vertex is of degree 2 or less. Then what I can do? Then what will I do? Three is degree. Yes, right. So if every vertex in a graph is degree 2 or less, what can I say about that vertex, that graph? It is like if the maximum degree is 3, that implies the graph is a graph such that every component, it's either a path or it's a cycle, right? It can be a cycle also. It's either a path or it's a cycle. And you know how to find maximum independent set in a path or cycle. You can, if it is an unweighted graph, you can just pick alternate vertices. If it is a weighted graph, you know, you can use a dynamic programming algorithm. All right. So that is polynomial time, right? Okay. So if you don't have a vertex of degree 3, then the problem can be solved in polynomial time. Okay. Otherwise, you can always find a vertex of degree 3. So what can I say about the recurrence now? So I can say that d of v is greater than or equal to 3 always, right? So my recurrence becomes t of n is t of n minus 1 plus t of n minus 4. This solves to 1.38 to the power n. See, there are some polynomial factors here, because at every step you are checking the neighbors, deleting the neighbors, and so on and so forth. But that can be done in polynomial time. So I'm using this notation which hides the polynomial factors. Okay, we are only looking at the exponential factors in the function. Okay. So our brute force was 2 power n. We improved it to 1.38 to the power n, which is a significant improvement. Yeah, it's not a constant sized improvement. It's, in fact, it's an asymptotically better improvement from 2 power n to 1.38. And that was our aim using branching. In fact, you can do, please ask if there are any questions, please ask. Okay, so there are more sophisticated branching algorithms which can improve the running time of maximum independent set problem to, or which can solve the maximum independent set problem on a general graphs in 1.2 to the power something, 1.2 some 1.28, I think 1.28 to the power 8, not 27. I'm not sure. But this like, it's a very simple algorithm. The idea is this, right? So you take a vertex, you branch on these two options. So if this is fine, we'll move to the next. Okay. Probably the first NP complete problem that you have seen, the 3-SAT problem. Okay, so I hope all of you know what the 3-SAT problem is. You are given n variables, let's call them x1, x2, etc. And CNF formula. There are m clauses and it's 3-SAT, right? So that means every clause has 3 literals. Okay, so if you are given x1, x2 up to xn, so everything is of the form x1 or x2 or x3, something like that. You can even have something like x5 or x, 2 also. This is also fine. Okay, the number of literals in a clause is at most 3, and you have m clauses. And the question is, does there exist an assignment that satisfies this formula? The classic, maybe the first NP complete problem. Okay. So how can we solve 3-SAT using brute force? Try all assignments. Yes. Okay, so for every variable, you check whether it is true or false. So how many assignments are there in total? So there are n variables. How many assignments? The 2 power n, right? So every variable can be either true or false, right? So brute force will give us 2 power n. Okay. Question is, can we improve this? Okay. Right. So actually what we discussed today is comparatively simpler algorithm, which will give only like small improvements. Okay. So how can we branch on this 3-sat instance? So where should we start? In a maximum independent set, we started with a vertex and we branched on whether that vertex is in the solution or not in the solution. In 3-sat, what can we do? First expression, clause. Yeah. Okay, I'll say, okay. So you can branch on whether a vertex is getting 0 or 1. Okay, right? Yeah. So, but what we'll do? So we'll start with n vertices. So let's say that x1 to xn, this is our instance. Okay, and we'll branch on the value of, let's say, x1, right? So you put x1 equal to true, and in the other branch, you put x1 equal to false. Okay. So what can you do when, okay, in this branch, when x1 equal to true, what can we do on the rest of the instance? Any clause which contains x1, what you do? It is satisfied, right? Any clause which contains x1 is satisfied. So this you can delete. Okay, so here what you will do is you delete all clauses that contain x1. Okay, right, because they are, when x1 equal to true, they are satisfied. What about clauses that contain x1 bar? You are putting x1 equal to true. So what happened to that clauses? So you have a clause x1 bar or something. Let's say x2 or x3. Okay, and you are in a partial assignment where this is true. That means x1 bar is false. So we know that this clause is not going to be satisfied by x1, right? So then what is the use of x1? You just delete. Okay, so this and keep this. Okay, so is that clear? Right. Okay. Yeah. So delete. So when you put x1 equal to true, delete all clauses that contain x1 and delete x1 bar from clauses, right? If it contains it. And if at any point, if every clause is deleted, if it becomes an empty formula, you can say true. Or if a clause becomes empty, you say false, right? And similarly here, when in the branch where x1 equal to false, you delete all clauses that contain x1 bar and you delete x1. Right. Okay. Okay, this is, and what is, so what do you do? What do you solve? In after the branch, below the branch here, you solve for x1, you have already assigned something, right? You solve for x2 to xn. Same thing here. The algorithm is correct, but what is the running time for this? What is a reduction in the input size? Here you had n, here you had n variables. Here and here you have n minus 1 variables, right? So that will be t of n is 2tn minus 1, which solves to 2 power n itself, which is exactly the brute force. So even though it's a correct algorithm, it's not doing much. I'll take the other, can we do greedy solution, trying to make it true? Backtracking, no. Clause reduction, yes, we can do this. Trivial cases, like if there is something with x plus x bar, then it is going to be true, such we can, okay, that we can always do. It's kind of a pre-processing that we can do. Yeah, someone says we start with first expression. Changing or deleting the Boolean formula, there will be some time, but it can be done in polynomial time. All these additions, you're deleting the clauses that contain something or deleting something from a clause, that can be done in polynomial time. Right. Okay. Yeah. So as someone suggested, instead of starting with a variable, what if we start with a clause? Okay. So let's say in the formula, the first clause is, let's say, x1 or x2 or x3 bar. Okay. Right. So if you just look at x1, x2 and x3 bar, or if you just look at x1, x2 and x3, how many assignments are there? In how many ways can you assign x1, x2 and x3? 2 power 3, 8, right? So there are 8. Out of which, how many assignments will make this false? There is only one assignment will make this clause false, right? So you put x1 equal to false, x2 equal to false, and x3 bar equal to false. X3 bar equal to false. That means you put x3 equal to true. Right. So this is the only assignment that will make this clause false. All the other 7 assignments will make this clause true, right? Therefore, in a true assignment, you should take one of these 7 assignments, right? And we branch on it. So this is the algorithm. So for a clause, there are 7 assignments that satisfy the clause. You branch on all these 7 assignments. Okay? So basically, you start with your formula, and there are 7 branches. And in each branch, you have take x1 equal to something, x2 equal to something, and x3 equal to something. And in the child here, you have already assigned values for x1, x2, x3, right? So here you have n minus 3 variables remaining. And that is true on every branch. Okay. So what will be the running time of this algorithm? It will be T of n is 7, T of n minus 3, which is 7 to the power 1 by 3 to the power n, which is 1, which is better than 2 power n. It might take some time to be convinced that, okay, but there is a lot of difference between 1.9 power n and 2 power n, but believe me, there is. Because n is a large growing function, right? So we have improved using and the technique is very simple, right? So we just branched on, take every clause and branched on it. So we got a 1.9 power n. Again, as I said, there will be some polynomial factor here. We are ignoring that for now. We are only looking at the exponential function. Okay, fine. So if there are any questions, please ask now. Moving forward, we'll try to improve this 1.9 power n to something smaller than 1.9 power 1.9. Again, so let's take a literal. Yeah, so let's start with a clause. Let's say L1, L2, L3 are literals. Okay. Instead of branching on all the 7 assignments, we'll broadly classify these the 7 assignments into three classes, right? We look at the clauses where the first literal is true. We look at the clauses where first literal is false and second is true. And finally, we look at the assignments where first and second literals are false. The third one is true. Okay. And we branch on it. So what about the assignments like when first and third are true and second is false? Are we ignoring that, or are we considering that? Do you understand? Let's see an example. So let's say that, okay, we'll go with x1 or x2 or x3 bar. All right. Okay. They will be inside the model. So on one branch, we'll put x1 equal to true, right? But we haven't assigned x2 or x3. Okay. So here, so we started with n variables here. Here we have n minus 1 variables more. Now we reach here. Okay. And here we put x1 equal to false and x2 equal to true. So we have assigned, you have given assignments to x1 and x2. So this will be n minus 2. And on this side, we'll put x1 equal to false, x2 equal to false, and x3 bar equal to true. That is x3 equal to false. So this will be n minus 3. For each of these assignments, we'll do the other steps, the polynomial time steps, like whenever something is true, we delete the clauses that contain it and delete its opposite. So basically, this is our algorithm, right? So we recursively solve these three subproblems, which are of size n minus 1, n minus 2, n minus 3 respectively. So the running time of this algorithm will be T of n is T of n minus 1 plus T of n minus 2 plus T of n minus 3, which solves to 1.8 to the power n. Okay. So we have improved from 2 power n, which was the brute force, to 1.8 power n. Again, there are more involved branching algorithms, which improves, I think the best known algorithm is 1.6 to the power n. Best known. Okay. Okay, so this was 3 sat. What about 4 sat? I think that's something that you can think about later. Okay, what is the best running time you can get for 4 sat? That is, every clause has at most 4 literals. Can we solve 4 sat also using the same idea, and what will be the running time? Okay. Yeah, so that was our first technique. 4 sat converted to 3 sat by adding, but then you're adding variables. How will it, you have to work it out. I don't think it is the same algorithm, the same running time. It will be difficult. When you are increasing the size of the input, it will change. Yeah, you can do that. You can, yes, you can take T of n minus 1, n minus 2, n minus 3 plus n minus 4. That's how you can extend the same idea. The running time will be worse than 1.8 power n. Okay. But again, maybe I should mention that according to a conjecture or according to a hypothesis, if you are considering k-sat, that is a sat question where a clause can be k, and when k is very large, when k is much larger than a constant, then 2 power n is the best possible. You don't expect, again, it's a hypothesis. It's called strong exponential time hypothesis. It's not proven, but it's considered to be true by the community. Okay. But for 3 sat, 4 sat, 5 sat, and you can improve the running time from 2 power n to something. Okay. So that was the branching technique. Let's quickly move to the next technique. Yeah, I think you have seen dynamic programming in your first course in algorithms, right? Okay. Now we'll see how to use dynamic programming to get exponential time. I hope all of you remember what are the basic elements of dynamic programming. You always look for you solve a problem by solving subproblems. That means you're assuming there exists some kind of optimal substructure. Okay, there is a question. Be as bad as 3SAT? Yes. Okay, I think that's a very good question. Okay, so 3SAT is considered to be NP complete, and you know that every NP complete problem is reducible to another NP complete problem, right? So you have seen that, yeah, so you have probably have seen it. So you know that 3SAT is NP complete, 4SAT is also NP complete. So, and therefore, you know that 3SAT is reducible to 4SAT and 4SAT is reducible to 3SAT. So how is it possible that 3SAT has a particular time complexity and 4SAT has a worse time complexity? That is the question. But then there, in these reductions, we are spending a polynomial time. Okay, right. So you just have to look at, so you look at the reduction from 3SAT to 4SAT problem, you're spending some polynomial time where the degree of the polynomial is larger than 1. Yeah, so because of that. So this reduction means that if if 3SAT admits a polynomial time algorithm, then 4SAT also admits a polynomial time algorithm. That is the meaning of that reduction, and vice versa. But it doesn't say that, but that doesn't transform to exponential time times. Okay, great. I think 3SAT and 4SAT are the same. That's, I think I answered that question. There is a reduction from 4SAT to 3SAT, right? And you spend some time there. If you try to, if you try to go over that reduction and assume that, okay, 3SAT has an algorithm of this, and then what does that reduction give you for 4SAT? It's not very difficult to see. Maybe different in the base. Yeah, again, that's what I said. Since 1.8 power n and 1.9 power n, they are not asymptotically the same thing. They are the base of an exponential function, right? So they are asymptotically different also. But you can say that if there is a reduction from 3SAT to another problem, which takes only linear time, then no, I think you need better than linear time. Okay. Then some of the running time complexities will go through. Okay, right. So you have to look at the reduction and kind of reverse engineer the reduction to see the action. Okay, yeah. But I'm happy that somebody asked that question. Okay. Okay. Yeah. Back to dynamic programming. So this is like a fresh topic again. Yeah. So dynamic programming, you know that there are certain elements like, okay, you are solving sub-problems. So you're expecting the problem has what you call as an optimal substructure. That is, you find an optimal solution for a sub-problem. It can in some way be used to find a solution or an optimum solution for the full problem, for the entire problem, the bigger problem, right? So, okay. So here also we are using that. The main difference from the problems that you have seen, the shortest path and all, is usually in polynomial time dynamic programming algorithms, you only have a polynomial number of subproblems. Here the number of subproblems can be larger or it can be exponential. Right. So let's start with the graph coloring problem. Okay. So the graph coloring problem, you all know you are given a graph G and you want to assign vertices, assign colors to the vertices such that two vertices which are adjacent, that which share an edge, should get different colors, right? So more accurately, this is called proper coloring of graphs. But in this talk, when I say coloring, I mean proper coloring itself. Okay. So when you are given a graph and you want to color them using, you have to color the vertices such that adjacent vertices have different colors. And the question is, what is the minimum number of colors that need to be used? You want to minimize that. That's a graph coloring problem. So graph problem is another very infamous NP complete problem. It is very tough even on some simple graphs. Whereas, okay, that is for a given graph, checking whether it can be proper colored using 3 colors itself is an NP complete problem. But you can check whether a graph is 2 colorable or not, can be proper colored using 2 colors or not. That is polynomial time solvable, because what are 2 colorable graphs? They're exactly what you call as a bipartite graph. And you can check whether a graph is bipartite or not using your DFS, BFS. Okay, so that is polynomial. But for k greater than or equal to 3, it is NP complete to check whether a graph is 3 colorable. So here we are considering the question how to color a graph using minimum number of colors, or how to find what is the minimum number of colors needed to proper color a graph. Okay, good. Right. So what is a brute force algorithm? How much time a naive algorithm will take? So how will you check it? Okay, suppose you are solving 3 colorability. That is, you're checking whether a graph is 3 colorable or not. How will you check it? Brute force, by brute force. For every, you consider every possible recoloring of the graph and check whether it is proper or not. Right? And yes, as you said, every node or every vertex has 3 choices, 3 colors that it can take. Three colors it can take. So therefore, it is there are 3 power n 3 colorings. You have to go through all of this. So that is for 3 colorability. In general, if you want to minimize the number of colors, you probably have to check for 3 colors. And if 3 colors does not work, you check whether 4 colors will work, which can be done in 4 power n time. Again, you check for 5 power n and so on. So you can say that it's roughly like n power n is a brute force algorithm. We'll try to improve it to something better. Okay. So the idea is to use dynamic programming. Okay. So in dynamic programming, you know that, okay, you want to somehow use the property of optimal substructure. That is, so you have a graph. Okay. Can it help if I know how to solve a subgraph? Okay. If I know how to color a subgraph using minimum number of colors, will it help to color the entire graph? Okay. Suppose, okay, so maybe I can say this, right? So, okay, so I'll take let X be a subset of vertices, and let opt of X is the minimum number of colors required to proper color G of X. Okay. Okay. So if I know opt of X for some X, so I take a subgraph, all right, and I take a super graph of this, right? So I add some more vertices to it, right? Can I solve this now? Okay. So let's take this. So you have given a graph and you're trying to color it using k colors or minimum number of colors, whatever, right? Okay. So I'll take the first color. I mean, there is nothing any color I can think of as first color, right? So I'll tell you, okay, so you have a graph and these are the vertices which are colored using color 1. I give you that. Okay. So I tell you, okay, these vertices are colored using green color. Obviously, they are going to be independent. They cannot have an edge between them. But what will you do about other vertices and the edges between them? See the graph remaining, the graph except the green vertices, it's a smaller graph, right? So you can solve it as a, you can think of it as a sub problem and you can solve it. But it is dynamic programming, so you don't solve it recursively. Recursion might not be a good idea there. But you build up from smaller graphs, you color smaller graphs, then use that result to solve larger graphs and so on. Okay. That's it. Right? But how do I get the green set of vertices? The first color. Okay, is this much clear that if I know the first set of vertices, if I know the color of, or if I know which vertices are colored using green color, and the remaining vertices are the remaining graph, I can color using my optimal subproblem, that property. Okay, but how do I get the green set of vertices? Vertices with green 0, with degree 0, I mean, okay, then they are not very interesting. Yes, it's okay. No, they might have edges. I mean, they are not vertices of degree 0. Your graph is like this. They are not degree 0 vertices. Right? Okay. Yeah, coloring class, a color class is an independent set. Yes, right. So I know this is an independent set. Okay. But there are many independent sets in a graph. One of them is my color class. I know that, right? So I go over every independent set in the graph. Right. So this is how. So if opt of x, it gives the minimum number of colors required to proper color subgraph. How can I find? So I'll look at I, right, where I is an independent set. Okay, I go over every I, and at every point I'll take I and I'll consider, okay, what if this is my first color class? How many more colors I need? That will be given by opt of x minus I, right? And in the second case, I'll take another independent set and I check, okay, what if this is my first color class? Then I solve the remaining problem. And I go over all possible independent sets or all possible values of phi. Right? So is the property or is the correctness of this formula clear? So you start with x. So when you put x equal to the entire v, that's the solution that you are looking for. Where exactly are the sub problems overlapping? Right. So you might have the same set of vertices in multiple places, right? So you start with a graph. Okay, so let's say that you are coloring this, right? So for this, I mean, this can, so for this, if you take this green set and so this is my green set, then I have all these vertices here, right? And from here, I'll take maybe these vertices are something, I've assigned some other colors and this will come. And I can start with any other independent set and this can still come. Okay. So every subset, if you take I mean, in the worst case, every subset can appear in a number of branches. Okay. Hope I answered your question. Not taking a maximum independent set. Yeah. So why should a maximum independent set be a color class? We only know that an independent set is a color class. A color class is an independent set. It does not mean a maximum independent set is a color class. Actually, you can build examples for a maximum independent set. It's not. Right. So, yeah. Okay. But you can say that about a maximal independent set, that we are coming to that later. Do approximation algorithm work for graph coloring? Yes, of course. I mean, this you can look at. I don't know what is the best approximation algorithm known for graph coloring. You can ask Prof. But there are like for example, there is this greedy algorithm which will give you a approximate chromatic number. Okay, yeah, but using I think that was your question. Okay, yes. So here again we start with small sized subgraphs, and we'll compute opt of x for x starting from size 3 and finally n, and for each of them we use okay. What is the running time of this algorithm? Is the algorithm clear, or is the correctness? Are all of you convinced of the correctness? Okay, please ask if something is not clear. Okay, right. What is the running time of this algorithm? So x is every possible subset of V. So that is 2 power n, and I is also every possible subset of x. Okay, it's not every possible, it's a independent set, subsets which are independent set, but again upper bounded by 2 power n. So this becomes 4 power n. I mean, it's still an improvement from n power n that we started from. We can actually count it a little bit more carefully here. That is, see, x is okay. So x goes from size I 3 to n. So you can think of it as summation I is from 3. I mean, there is nothing special about 3. You can start from any constant and then n choose I, right? This will give you x. Okay, and I is what? Subset of x. So this will be 2 power n minus I. So this is the running time. This is actually slightly better than 4, not slightly, it's better than 4 power n. It is actually 3 power n. Right. So the same algorithm, you can analyze it a little bit more carefully to get 3 power n. Okay, right. In fact, you can change the algorithm a little bit more. See, you can always say that here I said I is an independent set. I can always say that I is a maximal independent set, not maximum, maximal independent set. Independent set which cannot be extended more. You cannot add more vertices without disturbing the independence property. That is a maximal independence. Okay. We know minimum number of colors are 1. Okay, so to answer that question, yes, if you binary search, like let's say you're checking for some k in that range, how will you check whether k is the right answer or not? You have to spend k okay, you still have to use something similar to n power n. Of course, you can use this algorithm. Right. Okay, so in the next, okay, here we'll say that we'll slightly modify here, saying that instead of I, which is an independent set, we'll take a maximal independent set. Now, why is this useful? Because we have this result that this result that we can use this result that graph with k vertices has at most 3 power k by 3 maximal independent set. That's also we have seen branching, so you should be able to prove this if you put some thought in it. Okay, so yeah, so now we know, going back to the running time, instead of 2 power n minus I, here you can use that. Okay, there is 3 power I by 3. Okay, so the running time will become 1 plus, so this will be 1 plus 3 to the power 1 by 3 to the power n. Okay, so which is 2.44 to the power n. Oh, see here, this recurrence, it's for finding an optimal number of colors. I'm not checking for a given k whether it is k colorable or not. For every subgraph, I'm finding what is the minimum number of colors required. So yeah, don't know how to use a binary search type of things. Okay. Okay. So I have like 20 minutes. So maybe I'll skip. I had some more. Okay, maybe I'll skip this. The other dynamic programming algorithms. I'll just go over it. Okay, so you can see the traveling salesman problem again. It's by brute force is n power n. Using dynamic programming, you can improve the running time to 2 power n, and I think that's the best known for a general traveling salesman problem. This result was published in 1960s, but I mean, still it's the best running time now. Okay, right. And next one was set cover problem. Maybe I'll skip through it because I want to show one more technique. Second, algebraic techniques, exact exponential algorithm using algebraic techniques, a broad topic. We'll see only one tool here, which is the inclusion exclusion principle. Okay. All of you have seen this in your maybe class 7 or class 8, that if A and B are sets, then cardinality of A union B is cardinality of A plus cardinality of B minus cardinality of A intersection B, right? If there are more sets, like there are 3 sets, A union B union C, then what is it? This is cardinality of A plus cardinality of B plus cardinality of C minus cardinality of A intersection B minus cardinality of A intersection C minus cardinality of B intersection C plus cardinality of A intersection B intersection C, right? Right. Okay. So this is the inclusion exclusion principle, or it's the more general version. So if you have n sets, A1, A2, An, then the cardinality of union of so this is cardinality. It's supposed to be larger. Okay, so cardinality of union of all these sets, it's given by so this is basically n. So this notation means X is the set 1, 2, 3 up to n. Okay, this is what we mean. Okay. And you take every subset of this, you're starting with null set. Okay, basically what you're doing is you're taking sets 1 at a time, then 2 at a time, 3 at a time, and so on, and appropriately adding or subtracting their intersections, the common intersections. Okay, right. Okay, fine. So this is inclusion exclusion principle. Now, again, this is like, basic high school mathematics. We'll see how we can use this to solve our graph coloring problem in better than, what was the running time? We had 2 power 4 to the power n algorithm. We'll try to improve it. Okay. So using De Morgan's law, you can write inclusion exclusion principle as an intersection version also. That is, the cardinality of intersection of AIs can be written as a long formula which involves intersection of complements of sets. Okay. I mean, it's very, I hope you might already know this. Otherwise, it's not very difficult to see it using the union version and De Morgan's law. Okay. Okay. Right. So just keep this in mind. Let's go back to our graph coloring problem. Right. Question is this: given a graph G, is G K colorable? Let's assume that K is given to us, right? So we are checking whether K. Right? So what if K is not given to us? As you were mentioning on the chat, you can work for all possible values of K and do a binary search. Standard techniques. Right? Okay, let's assume that your question is given a graph whether they can be colored using K colors. Right? Okay, or so this can be written in different way, right? So instead of asking K colors, you know that in proper coloring, a color class is an independent set. Okay, so coloring using K colors can be equivalently written as covering using K independent set. Right? So let's say you have a graph which is colored using, let's say, 3 colors. That means, yeah, so I don't have edges between same colors. So I can think of this as covering all the vertices using independent set. So I take this, so this is an independent set, and I take this, okay, this is also an independent set. I take these two, this is also an independent set. Okay, right. So I'm going to state the K coloring problem as covering using K independent set. Okay, right. So we are going to use inclusion exclusion principles. So there should be some universe and some sets defined on the universe, right? Okay. So our universe is this. Okay. So we look at every independent set in the graph. Every independent set. I'm not saying maximal or anything. Every independent set. Okay. And the universe is tuples of, or K tuples of these independent sets. Okay, so let's say that, okay, so I should say, so it is, so U is, okay, should we give an example, right? So let's start with this graph itself. I'll call it A, B, C, D, E, F, G, H, right? So I have, let's say, one independent set, like for example, if I take A, C, G, it is an independent set. I take I2, do I need to take maximal? No. So I2, I'll take, okay, B, E, H, okay, this is another independent set. And I3 again, I take B, D, etc., right? B, D, H maybe, okay, right. So likewise, I have a lot of independent set, and I'll consider K tuples of it. Okay, so I have like, you know, I4, I5, etc. So I'll take, let's say, K tuples. So take K equal to 3. So my universe is, okay, it contains tuples which contain 3 independent set. So I have, so I1, I2, I3 can be is in the universe. Also, there is, I can even repeat. So I1, I3 is also a tuple. I1 is also a tuple. And I2, I3, I4 is a tuple, and so on. This is my universe. Okay, right. So there can be overlapping, there can be repetitions, it's all possible, right? Okay, so that is my universe. So universe is K independent set. Okay, tuples containing K independent sets. Okay, now I have to define union of k independent tuples, right? Okay, yeah. So, but these tuples I haven't even covered every vertex yet. So, okay. And in the universe, I define sets like this. So for every vertex, I define, for every vertex V, you can define a set AV as a tuple that covers V. Right? So this is a formal definition. AV, it's a tuple of k independent sets such that V is in at least one of these independent sets. Right? Okay. Okay. So how can we write this for as a graph coloring question? So we have independent set. Every k tuple is k independent set. What is the extra property we needed? We need every vertex to be covered in this k tuple, right? So this is exactly this. Okay, so AV, it is k tuples where V is covered. Now you find AV for every vertex V and take the intersection. That means you have any set in that, okay, or for every vertex is covered by one of those independent sets. There may be more than one of it. That's why we are saying that every cardinality, or sorry, every k tuple in the intersection of AVs, it represents a valid k coloring. And cardinality of AV is basically gives you the number of k colorings of V. I'll give you 2 minutes or give you a couple of seconds to understand this. So how do I solve whether a graph is k colorable using this? If I'm able to find this, it will give me the number of k colorings. If it is not 0, that means the graph is k colorable. Okay, and is that clear? Okay. And how do I know? How do I find this? I'll use inclusion exclusion principle. I use this formula. Okay, and so here what do I have to find out? I have to find these values, right? Yeah. So basically, yeah. So for every AV, I have to find U minus AV. Okay, right. Basically, I have to find the cardinality of U minus AV if I have to find this. So this can be found in polynomial time. This is basically, you have to count how many independent sets are in V minus AV, and can be found in polynomial time. So you can find all these values in polynomial time, and then you use inclusion exclusion principle. So how many terms are there in the expansion of inclusion exclusion? There is 2 power n. So every value of U minus AV, cardinality of U minus AV can be found in polynomial time. I'm skipping the details there. I think, yeah, I have it. So if you want to compute U minus AV, so this is the number of independent set in G minus V whole to the power k. This will be the cardinality of U minus AV. And the number of independent set in a graphs you can find in polynomial time. Okay, so you find this in polynomial time, and you find this also in polynomial time. So you have 2 power n values in inclusion exclusion principle. You have to do like plus minus whatever, right? So each of these values can be computed in polynomial time, and then you do a sum subtraction, addition, whatever. So that can be found in 2 power n time. I know that this the final algorithm. I know I went a little fast, but yeah. Okay. So some so we have seen 3 techniques: branching, dynamic programming, and in algebraic technique itself, you can use, so inclusion exclusion principle is one of the basic techniques that you can use. There are fast other methods like fast subset convolution, then a lot of others which I don't think I'll be able to cover here. Yes. Traveling salesman problem. No, traveling salesman problem, I had a dynamic programming algorithm, which I don't think I will be able to cover now. Tomorrow's talk, I don't think I'll be covering any traveling salesman problem now. I can let you know, or give you suggestions to read if you want to see traveling salesman related. Yeah, that's a 2 power, that's 2 power n itself. I can give you the reference for traveling salesman. Just you can ask me in the Zulip chat. I'll give the reference. Okay, and 2 power n is the best known algorithm for general. For special cases, there are better algorithms. Right. So I think we are open for questions. If there are questions, let's ask. Otherwise, tomorrow we'll be discussing parameterized algorithms, which has a number of similar techniques, but it's different from this. Thank you for your attention. We'll meet tomorrow.
Thank you, ma'am. Thank you for the interesting talk on exact exponential algorithms. So we are concluding the first day of summer school on algorithms. Tomorrow we will have the session on parameterized algorithms at 10 a.m. See you all tomorrow. Thank you.